In previous lecture, we have seen that how to use this KD tree to find the k nearest neighbor. So we have seen these techniques, how to using this KD tree concept to find the k nearest neighbor. But there have many limitations of this KD tree. So let's see what are the actual limitations. So to find the KNN in by using simple KD tree, we have just if you remember. We are drawing the picture like that. Suppose let's take we have our query point is here. Suppose let's take our query point is here. Then for this query point we have to taken care for these regions as well as this one. So for 2D we have to, for 2D, if our query point is like here, so if you just take the worst case, so in 2D how many regions we have? 4 regions. If we consider the 3D, so how many regions here we have? So in such 3D, if you just taken the picture like that, in 3D our regions will be this kind of pictures. So in 3D we have three this kind of 3 planes. 8 means we have to compare for each point. Suppose if your point is here, we have to compare for 8 planes. So in a 8 planes, and similarly for ND we have 2 to the power n points, n number of planes we have in n dimensionals. In D n dimensionals we have 2 to the power n number of points. So if suppose if we have increased the number of dimensions, then what happens? So when D is not a small number, simply when D is not a small number, in D is a small number, suppose let's take our D is equals to just I am simply using some medium number. Suppose let's take our dimension is 10. So what happened? We have to compare the H 2 to the power D planes. So it's 2 to the power D means what? 2 to the power 2 to the power 10 means 1024. And if we take D is equals to 20, then what will be the D? 2 to the power, it's near about approximate equals to 1 million point, 1 million planes. We have to compare for one query points. So we see that if we decrease the value of D, then worst case, in worst case, this is the simply we have considering this case. In worst case, we have not considering this a best case. This we have taken these situations in worst case. If we just simple the value, increase the value of the D, then in worst case number of adjoint cells, number of simple these adjoint cells which increased as exponentially. Okay, means if we increase the value of D, worst case number of adjoint cells increased as 2 to the power. Okay, this is a huge number. This is a huge 1 million point. So if we have simple D is equals to 2, 3, 4, 5, it's okay. It's we can consider. But simple medium number, but simple just if you considering some middle number 10, then you can see how much the adjacent cells, how much increased. For worst case, how much comparisons we have to make. This is the not a good signs of this KD tree. Now another thing, and another thing is that the time complexity we have seen for the best cases. For the best cases, time complexity we have seen that time complexity is for best cases order of log n. We have seen it to find a 1 n point. Okay, and for worst cases, this is how much for worst cases. For worst cases, we have seen this. For worst cases, it will be increased 2 to the power D into for kn or if we have considered d-dimensional space, suppose we have considered d-dimensional space, so it will be converted into 2 to the power d into log n. Okay, and this is approximate equals to order of d. Suppose let's take our 2 to the power d approximate equals to d, n, order of n, number of data points. So this thing will be what? This thing will be transferred to order of n log n. So in brute force, it's simple. We have taken the simple kn, and here we have seen in simple kn, and we have seen our time complexity is order of n for simple knn. But if we consider the KD tree, then we can just for a large number of for large d, we can see that the time complexity increased so dramatically. It is order of log n. In simple order of log n, you can see. So order of log n is always larger than order of n. So this thing is worst case. If we just take in the simple knn, it will be then better instead of KD tree. So the time complexity here. So the time complexity increased here dramatically, extensively, exponentially. Okay. So the main problem is for this KD tree is when we have increased some regional small value of d, then what happened? Then time complexity increases dramatically. Then this time complexity increases dramatically. Okay, I think you will understand this thing. Now the one thing, another this is one main problem, time complexity. The another main problem here is the if our data is not uniformly distributed. Suppose let's take, we have seen that the in the second problem, this is the first problem. This is the first problem. The second problem is that suppose let's take our data is not uniformly distributed. So suppose let's take uniformly distribution means so what? So data is means what? If our data is look like that, then it is chances that it will be spreaded everywhere of our plane. Everywhere. This is the chances. This is simple the uniformly distributed. This calls mean this is the simple uniformly distributed. But if it is not uniformly distributed, then this data will be look like some clusters of our plane. Look like some this one is some clusters. There I have making some clusters. There I have making some clusters for this data. So look like that. Look like that. These clusters means here not uniformly distributed. Not uniformly distributed. This means, so we have seen it uniformly distributed. If your data is uniformly distributed, then the best cases, in the best cases, in such best cases, our time complexity is order of log n. We have seen this thing, but just simple, if your data is not, if real world data, we will see this thing, this kind of situations only occurs if our data is not uniformly distributed. So in such situations we have make this kind of comparisons, we have make this kind of worst comparisons. So in such scenario our time complexity increased to as order of n, approximate as equals to order of n. So this thing as compared to order of log n, if this is not, if this our data set is not uniformly distributed, So these things, our simple, our we have seen our simple implementation of the KNN. Simple KLN is order of taken the order of order of n time. Order of n time is taken the simple KNN. But if we use the KD tree to search the nearest neighbor, then we will simple. If your data is not uniformly distributed, then the time taking is taken order of n log n. If our dimension is large one, so these things is not a good symbols. Okay, so these are the limitations. Some limitations. There have also many limitations, but this is the major to most limitation of the KD tree. Because of that, we have not in general considering the KD tree in our classifications, in the classification. But the most useness of this KD tree is computer graphics. If you just see this thing, our computer, if you just see the 2D computer graphics in our simple, just we have to play the computer graphics is like a 2D plane. So in such scenario, KD tree is very useful in simple computer graphics. In computer graphics, it is very useful. Okay, and the invention, the invention of this KD tree is look like for the computer graphics, mainly for computer graphics. It is not for machine learning classifications. Okay, I think the limitations of these two major limitations you have understand.